Maybe I need to go over there, just so I don't feel so dumb all the time.
How's homework one? Good? Fine. The data loader didn't screw everyone up. Oops. Good thing to know for next time. Did anyone implement the diffusion policy? Give it a try. It's fun. Yeah, Jacob stole a lot of code from the diffusion policies, like official code base, but it's like actually all single file is nice. Um, yeah, try it out. Any suggestions for things you all want differently for the next time around for homework one? We're always looking to improve. Well, data loader, we need to fix the data loader problem, but yeah.
Good question. Is it possible at all to run Joko on, say, like Windows machines?
It's a huge pain. It's a huge pain. I think it is possible, but it is actually Windows is better than Mac. Um, but because Emo ran a lot of his stuff on Windows. I think Mujoko will run. I don't know if the like Python interface will run. I can try, but I haven't used Windows since like the early 2000s. So, yeah. I'll give it a look. Okay, so first thing before we get started, I was thinking about Sid's question from earlier about like last class we had discussed PPO, where we had this objective which was like min of advantage times like pi theta by pi theta old. And then you have this clip function of, let's call this thing ratio 1 minus epsilon, 1 plus epsilon times advantage, right? And there is this question that is brought up and like, why is why is the clip inside the min and why is the advantage being multiplied? And if like, if you're always clipping, if the ratio is always being clipped between 1 minus epsilon, 1 plus epsilon, isn't this useless? The answer to that is because your advantage can be positive or negative, right? And so if it's positive or negative, then you kind of you can't say which direction it's going to be flipped because the sign will change. And taking the min is basically trying to take a lower bound, like take the lowest possible thing and like push it up, right? So it's trying to say we'll take a lower bound on the objective and push the lower bound. And so the reason we do the like flip inside the min is so that you can always take a lower bound and push that. So that's why we do that, just for anyone who's thinking about that, because I thought about it. Cool. All right. So now we are finally done with policy gradient. And if you want to use model free RL for like applied problems, you like have a problem you want to like do chip design, I recommend using PPO. Like PPO is the algorithm that will work the best, in my experience. But it's not going to work in certain domains that are data scarce. It's not going to work on a real robot. It may not work on neural engineering, maybe where you have sparse data. Like you need things that are more efficient, and things that are able to use prior data. It may not work well when you're bootstrapping from like in healthcare domains, you have like lots of pre-existing data that you want to use. So the next set of methods we're going to discuss, which is ADP and model-based RL, will try to like both be more efficient and be able to better use prior data, right? And so that's kind of what the next section of the class is going to talk about. So our outline for today, we're going to start by thinking about off-policy RL motivation. We'll talk about some practical tricks to get actor critic to work in practice. And likely we won't get to the last two, but those are a little more questions about theory and like whether this thing converges and some frontiers. Yeah, cool. So at least the way I think about off-policy RL is like I'm a roboticist, so I think about how do we make policy gradient methods suitable to run directly on a robot. So if I want to train a robot in the real world, how do I get a reinforcement learning algorithm that I can actually run? Right. So if you look at the PPO numbers, it's like 2 million samples, and 2 million samples is several days of robot time, right? And so how do I bring that down to 10,000 samples, which is a few hours of robot? And so that's kind of the motivating question here for off-policy RL. And so we want to start by thinking about why is policy gradient sample inefficient? Thoughts? What makes policy gradient inefficient? Credit assignment, yeah, good question. So, or good point. Like credit assignment is really tied to the problem of variance. Like basically, you have like a multiple step process, and you to figure out which things matter, you have to take many samples. This is a variance problem. What are other things that make policy gradient inefficient?
If you don't use the dynamics of the word, you don't have that, you can't just hallucinate like you can't hallucinate what might work better.
You can't hallucinate what might work better.
Like if you had it, then you wouldn't need as many.
Yeah, so in some sense, what you're suggesting is like counterfactual reasoning. So you're saying like, this is what I did. What if I tried something else? Yeah, so there's a certain element of that in that you only use your latest behavior to update things. You can't ask like what happened if I had different behavior. Off-policy RL doesn't fully solve that problem, as you can't ask arbitrary questions about the world, but you can ask questions more than just your current policy. Yeah, that's a good point. So those are basically the 2 points, right? So the first point is that it's on policy. So you're unable to effectively use past data. So you have a corpus of data, whether that's from past policies, whether that's from someone running experiments, from demonstrators. It's not clear how to use them well in policy gradient. And that makes it hard to ask these counterfactual questions, like what would happen if I had a different policy? And then the second is various, right? Which is essentially the credit assignment problem. If you have a multi-step problem, it's hard to know which of your actions mattered or which of the changes mattered. And so like those are the 2 issues that I think kind of like plague policy gradient. And so what we're going to try and do is try to develop a low variance, which means that you're going to like be able to learn with way less samples. Off policy RL, which means you can like try using things that are not from your latest policy, right? So off policy just means it doesn't have to be from pi theta current. So PPO is like a little off policy, but can we be way more off policy? And bootstrap it from lots of prior data. And so the next lecture or 2 will be basically trying to develop a low variance off policy RL algorithm. Yep. Okay. So if we wanted to like lower variance, right? So if you remember, the issue with variance is that you have a single sample estimate, which means you're just taking the sum of rewards in your current trajectory. And we said, okay, we can try and lower variance by subtracting a baseline, making it reward to go, like these things helped. Right. So we said we're gonna like switch from reward on this whole thing to reward just from here. And we're gonna like subtract a baseline to like deal with the scale issues, right? And so those are some things. But what else do we really want to do? Like, what is it like? If you think about the intuition of policy gradient, you're trying to increase the likelihood for actions which are good in the long term, right? So this is like measuring how good an action ATI is at state STI. And this is saying like increase its likelihood, right? And so this is like, you can think of this as a measure of goodness. And this is like saying max likelihood. Ignore my handwriting. But that's a single sample estimate. So if you wanted to do more than a single sample estimate, how might we get there? How do we do how might we do a non-single sample estimate? Like, let's not think about practical algorithms right now. If you wanted to like be impractical, right? Like, let's say you like had lots of Oracle access in the environment, you could do whatever you wanted. You could reset anywhere. You could try things over and over. Like, how might we get a better estimate? And so policy again, that we described is like only assuming sampling access to the environment. You have to reset from the same initial state. So those are the assumptions, but for just a thought experiment, let's remove those assumptions. Like, how might we do better? Yeah.
Go back to your state and replay it.
Perfect. Right. So you go back to your state and try more things, right? So you're trying to say, hey, you had a single sample estimate. If you were able to reset to exactly the same state, then you could go back to that state and try multiple different things, right? And so in some sense, what you really want is like you're at some state, you took some action, and then you want to like play out multiple possible futures, right? So rather than a single sample estimate, you really want a multi-sample estimate, right? Now, why is this a problem? Well, as Rico just said, we have to like go back to that state. And in any continuous space, you're never going to go back to the same state, right? So the challenge with this procedure is like, so if you had resets, go back to the same state, run multiple rollouts. So if you go back and look at the TRPO paper, they have this algorithm called find in there. And essentially it does this. Like what find does is resets the things in your trajectory and does little offshoots off of them. But we can't do that, right? So what else can we do? Like what can we do? And now we've like, this is the intuition we want to get to. We want to get to a multi-sample estimate, right? So when I say multi-sample estimate, I mean, take this S, this A, and play out many, many possible futures, right? And then like average them. And you want to see what the average goodness is. But we can't go back to the same thing. So how could we get around this?
And we could use past letter to kind of estimate how good the state is.
Yeah. Essentially, you're going to go to function approximation, right? So function approximation says, hey, you'll never come back to the same state, but you'll come to states that are pretty close by, right? Or like, I'll never be like right here when I'm picking something up, but I might be like reasonably close. And what function approximation is going to try and do is going to share information across these instances, right? So I'm never coming back exactly here, but if I'm estimating something, if I'm estimating value for this, like for, if I'm going to like, let's call it, let's say you have a function that takes in a particular state and action and estimates its goodness, right? Because this is a learned thing, it has some generalization, and you can like train it across these three things, and the function approximator allows you to share information. Right? So it's saying that like you can train it on this, this, and this, and it has like reasonable performance around there. And so the magic in actor-critic algorithms is it's going to try and go from a single sample estimate to a multi-sample estimate, but it's going to try and do it with function approximation. Any question, Rick? Yeah.
What if your state is very high dimension, like star, you don't actually end up being very close?
Yeah, so that's what makes off-policy RL a little tricky. So like it works from images and so on, but I think it's hard to know what the metric is that makes things similar. And like right now, what we do is we just throw a neural net as our function approximator, and we hope that the internal features kind of put them together. But that may or may not happen. So a lot of the open questions in off-policy RL are like analyzing convergence in situations where you have nonlinear function approximators. So like the question of like in a high dimensional space with a complicated function approximator, will the right things be close? It's not necessarily true. And so we don't necessarily know that it'll converge. But empirically, it seems to be okay with neural nets. But like the honest answer is we don't truly understand the dynamics of off-policy RL with neural nets. It's like open question.
When you have a high dimensional state space and you're explaining some encoder, you force the encoder in the training process to like, you take the image and you perturb it slightly, and you're basically saying, well, this image and that image, because I only perturb it slightly, I'm supposed to give you a very small difference in output as well. So small changes in the input, small changes in the output. If you enforce that, would that not get you closer to?
Yeah, so you can impose things like Lipschitz continuity or like put spectral norm on it or regularize your model, and that kind of helps. But in non-smooth systems, it can also hurt because you're like not allowing the model to jump where it needs to jump. I think there's some amount of implicit regularization that happens when you have like a smooth, like our neural nets have some level of smoothness already. They're not like arbitrarily spiky usually. And SGD gives you some level of smoothness. And so those things help. But yeah, I think lots of folks have found that regularization can help too. But I wouldn't say it's like it's science yet. It's a bit of an art. Okay, but the intuition here is we want to get to a multi-sample estimate. We'll never get back to the same state, but we can learn a function approximator, which is going to take in your state, your action, and estimate how good that action is at that state over the long term, right? And so that is the essence of actor critics. If you want to think about going from policy grading to actor critic, policy grade, or okay, so actor critic in general is just like switching out single sample estimates with multi-sample estimates using function approximation. And that's the essence of it. I think actor critic is used in two different ways, which we'll cover in a second, but generally that's the essence, right? Whenever people say actor critic, switch out single sample with function approximation. Okay. Cool. So let's introduce some notation to try and study this, right? So the first thing we're going to introduce is something called a Q function, right? So a Q function can be thought of as essentially saying is the expected sum of rewards in the future, starting from the state S, taking the action A, and then acting according to policy pi, right? So it's saying that if this was your S, you take not an action according to the policy, you take the action A that is input into the Q function. So you're going to take an action A, and then you're going to act according to your policy, right? And so it's important that this thing doesn't have to be according to the policy. It is just an arbitrary action. And so you take your first state, you started the first state, you take one action, which is A, and then you act according to your policy, right? So it's like one step action followed by your policy. And you take the expected sum of rewards, so you like average things into the future, right? And so if you think about like what we were saying, this is like measuring how good S and A are in the future. In some sense, Q is like directly measuring how good S and A are in the future. It's saying that under my current policy, if I started at S, I took action A, like how good was it in the long term? Right? And so you can kind of think of a Q function, or this is going to be what we call Q pi, which is going to be the Q function when you start at S, take action A, and then act according to pi. Right? And so, yeah, think of it as essentially a drop-in replacement for this like sum of rewards. So the sum of rewards was telling you how good was ATI at STI. Now you can replace this thing by Q of STI ATI. So it's telling you how good was action ATI at state STI. Right? So it's the expected sum of rewards in the future, starting at ST, taking action AT, following policy pi thereafter. Right? And so the same as before, the expectation is because the policy can be stochastic and the dynamics can be stochastic. Yeah.
That assuming deterministic dynamics, or
No.
where's the transition?
I just like shorthanded it. So it's like it's and dynamics.
Okay.
It's like the same expectation as usual. It's just like policy and dynamics. Yeah, it's good. Good point. So whenever expectation sub pi, it always means policy and dynamics. But there's no escaping the dynamics.
Okay.
So it's just like the dynamics aren't really under your control. And so I just like shorthand. Okay, does that make sense? This is as a Q, like the concept of a Q function. So what we're going to do to jump a few steps ahead is we're going to learn a Q function. And so we're going to use a function approximator for a Q function that is going to let us do this like information sharing between states that are similar, but not quite the same, right? And so a Q function is going to be our measure of goodness. And it's going to be the expected sum of rewards starting at state ST, taking action AT, and then following the policy pi. Okay. Okay. Questions? Okay. Good. So essentially a Q function bundles estimates of long-term value across different S's and A's. And we're going to use the magic of deep function approximation to kind of help us share information across things that are similar but not quite the same. Right? Okay, so how are we going to get Q functions? The first thing we're going to try and do is we're going to just try and do Monte Carlo estimates. And so what a Monte Carlo estimate means is that you're just going to try and do sampling and supervised learning, right? So if you remember how we learned baselines for policy gradient, right? What do we do for baselines? We just took a bunch of samples, right? We took their sum of rewards of all the trajectories, and then we tried and regress from V of ST to like the sum of rewards, right? That's what we did. So we just said like, let's sample a bunch of things. Let's take a bunch of trajectories. Let's take their sum of rewards, and let's just do supervised learning to go from ST to the sum of rewards, right? And that's going to give us our like average sum of rewards, which is going to be our value function. What we call our value function or our baseline, right? And I'll explain why the value function is relevant in a second, but we can kind of use the same trick here to learn a Q function. We're just going to take a bunch of samples, and then we're just going to regress. Or for the baseline, we regress from ST to the sum of rewards. Now we're just going to regress from ST80 to the sum of rewards. Right? And so we're going to say we have big neural net. Big neural net takes in state and action as input and predicts return to go as output. Right? And so what we're going to say is we took a bunch of trajectories. Okay. For each of them, we're going to say at every S and A, we're going to compute the return to go. Right? So we're going to sum up the rewards in the future. And then you're going to do this for all the states and actions within a trajectory and do this across different trajectories, right? And you're going to come up with a data set of S, A, return to go, S, A, return to go, right? You're going to come up with a big data set. And then you're just going to do supervised learning. So you're going to say, I have a big data set of current states, current actions, and the return to go from my like samples. And you're going to try and learn a model that goes from like some QSA. That is like, you're going to try and regress from that into the return to go, taking an expectation over all your samples. And you're going to try and minimize this distance over Q hat, right? And so essentially, what you're going to try and do is just make this into a supervised learning problem. Right? So it's supervised learning problem because you do a bunch of samples, then you just learn a model that goes from state and action to return to go, right? That is your Q function. So
Return to go is the
sum of rewards in the future. Yeah. So when I say return, it's usually sum of rewards, and rewards are like one step and returns are multi-step. And so whenever we say like return is usually the whole return, the whole sum of rewards for a trajectory, and return to go is from your current state onwards. Okay. So that's what we're going to do. We're just going to do regression. What's the problem with just doing regression? So like, I mean, nothing seems crazy here. I mean, we're just doing regression. We want to get the expected sum of rewards in the future. We just took like a bunch of samples and we just did regression to go from S and A to sum of rewards in the future. Like all seems valid. Like what's the issue here? Why might it be a problem?
I think, but what if your reward is like only given to you at the end of the project? And so all S8 up to that point are just gonna have the same return to go. Would that be good?
Yeah, so like if you have sparse reward, then it's like hard to know which things matter, but that's going to be hard for basically any method. Part of the issue here is that, okay, so it's going to be unbiased, as in if you have enough samples from your current policy, this will give you what you're looking for. But it's high variance and it requires you to get data from your current policy. And so basically, if you look at this regression problem, you take SA return to go, SA return to go. All of this has to be drawn under phi theta. And so we say we have to draw all my data under my current policy. And so we talked about being off policy, but inherently this is on policy, right? Like I cannot estimate this without data from my current policy. Right? And so the first thing is that it's on policy. And the second thing is that basically you are like taking entire trajectories and using that to regress your Q functions. And so it has the same like coupling between actions. It has like basically how good this thing, like in every, like how good this transition is coupled with all the things in the future, right? And so it's less like this, and it's more like this, right? So it's less like you go back to the same state and try multiple things. It's more like you're trying many different states. And so as a result, you have something that's high variance because your fate is coupled to everything else that you see in the future. Right? And so ideally what we're going to try and do is we're going to try and use the temporal structure of the problem to make this lower variance. But the issue with this thing is you need, like in practice, you end up needing a ton of samples. And you have to get the samples from your current policy. So it's not actually solving our problems. It's neither off policy, nor is it low variance. Right? And so that kind of makes it hard. This generally makes sense. Like the problem is we don't want to take samples from our current policy, and we don't want to have to couple our fate to like the trajectory that we saw, whether it's unlucky or lucky in the future. Yeah.
Why did you try to make everything like a supervised learning problem? That just is not good.
That's the only thing that works at that. I mean, in some sense, like, what is it like? Where everything is maximum likelihood in some way. It's just like you're just trying to convert things into maximum likelihood. Here is because you're trying to like trying to solve some sort of a regression problem. Like you have to predict what the future returns are going to be. So some level, it's a supervised learning problem. Yeah. I guess the question is, what would the alternatives be? Right? You can do like generative modeling, but that's like distributional Q. It's like modeling a distribution of the Qs, but it's not that different of a problem. So at least the only knobs that I really know how to tune are like, how do I maximize likelihood by tweaking parameters? And so everything kind of boils down to something like that. Good question though. Yeah.
So with using functional approximation in this way is essentially deriving, if you wanted to get, let's say, an estimate of the taking an action at a given state, you could do some matching, like a propensity matching, to see the conditional probability of arriving at that state given, I guess, the previous states, and then try to get an estimate that way.
You could.
So is this the goal of the functional approximation, just to wrap that all into like one function?
Exactly. So you can share information better across states, right? Like in some sense, if you do like density estimation and like trying to figure out what the likelihood of getting to a state is, you have to use function approximation there too. And so like, it's like shifting where the function approximation is happening. But like this thing is directly trying to estimate, it's not trying to estimate state visitations. It's directly trying to estimate future returns. Right? So it's like directly getting to the thing you care about. But model-based RL is going to be more like what you just said, where you like try to figure out what the likelihood of getting to different states is. That's a good question. Okay. Everyone kind of following what a Q function is? Yeah, go ahead.
This might be a
No.
Do you ever get stuck at like some local minimum in the state? Like, if your Q values are like bad, then would your model just choose some suboptimal path?
Yeah.
Self-confident.
Yeah, a lot, often. So, there's lots of like, we'll get into some of the pathologies of Q learning type algorithms. But there could be local optima because of like neural net stuff. You're solving a non-convex optimization. But like the type of thing we're going to do for going forward is not actually going to be supervised learning, like Kunal was just saying. It's like actually something a little different than supervised learning. And that it's called fixed point iteration, which is like not quite supervised learning. And that has its own set of pathologies. And so with Q learning, you like tend to get stuck because like I feel like the neural net problems are not that much of a problem because we've kind of figured out how to do reasonable neural net optimization. But like the pathologies of the dynamics of Q learning are not the same as the dynamics of supervised learning. So we haven't gotten there yet. We'll get there in a second. But the algorithm I'll introduce on the next slide will have a different behavior than supervised learning. And we'll talk about that. But this algorithm, the reason, like this Monte Carlo stuff, like the reason it's going to struggle is because of variance and just like neural net optimization. Yeah. It's a good question. Okay. So can we do better, right? Can we do better than just doing Monte Carlo regression? Because Monte Carlo regression was both on policy and it was high variance, right? And so we want to be off policy and we want to be low variance, right? So we want to find a better way to estimate Q, and we want to do it off policy, right? And the key to kind of doing that is to leverage the Markov property, right? So if you remember lecture 1, we're talking about the Markov property. The past is independent of the future conditioned on the present. And so this class of methods, which we'll call dynamic programming, approximate dynamic programming, Q learning, active critic, like all of them are basically trying to exploit the Markov property in a clever way so that you can learn off policy and you can have lower variance. So just a reminder, what we're looking for is something that like does this, use a multi-sample estimate. What we're getting is something that looks like this, right? And so you kind of like, you don't share enough information between the things because you're like coupling your future to everything else in your current trajectory. Right? And what we're going to try and do is be off policy. So don't use your latest, and be lower variance. Yeah, that's our goal. Okay, so let's get to what we're going to do, right? So we defined a Q function. The Q function was our expected sum of rewards in the future, given our current state action and are following our policy pi, right? And so the next thing we're going to define is something we're going to call a value function. And we've already talked about the value function a little bit before, but a value function is the expected sum of rewards in the future, starting at the state S, but not taking the action A, instead taking the action A from the policy, right? And so the difference between a value function and a Q function is that a Q function takes the first action AT, and a value function takes the first action AT sampled from pi, right? So like you can think of a Q function as doing one step according to AT, and then following the policy pi. And the value function as just acting according to the policy, right? And so that's the definition of value function. It's basically the same as a Q function, except it's not taking the different action AT. Instead, it's just following the policy pi from the first step on. So how do I relate the value function to the Q function? So I defined the value function. I defined the Q function. How can I relate the value function to the Q function? Yeah.
It's like Q function is like what value you would get from the state at which you end up after applying the first action. Like you apply the first action,
Uh-huh.
and then after that, what is the value you would get?
Yeah. So yeah, that's how about let's start by writing V in terms of Q, and then we'll write Q in terms of V next, right? So if you were to write V in terms of Q, that's a simpler one. So like, how do I write V in terms of Q? Remember that V is saying it's all the magic is in this expectation. It's saying that like your first action is sampled according to pi theta, and your future states are sampled according to your dynamics, right? And here it's saying that your first action is AT, and your future actions are sampled according to your policy, and you're sampling next states from your dynamics, right? So if I was to relate the value function to the Q function, how do I relate them? Go ahead, Kunal. No, you can go, Kunal. Sum over Q functions weighted by the policy. That's right. So which is the expected Q function under your policy, right? So just saying like, you can kind of think of this as your Q function is saying act according to AT and then act according to your policy. It's just the average, it's like you take the average of the Q function according to the actions AT sample from your policy, right? And so essentially this is saying take the first action AT and then follow your policy. This is saying like average this thing over actions, the first action sample from the policy itself. And so you can kind of think of like this thing is doing it for the Q is doing it for a particular action. And then the V is saying, let those particular actions come from the policy, right? So V is equal to the expected Q. Does that make sense? So like, we're going to use this in a second, but essentially a value function is nothing but the average Q function. And then the other thing that's useful to think about is what Sid just said, right? Which is saying that like your Q function is in some sense the average sum of rewards when you take S and you start at S and take action A. And so you can say that the Q function, like you kind of think of like if there's a chain, your Q function is start at S, take action A, and then follow the policy pi thereafter, right? Which means that your Q function is like your reward at your first step, right? Plus the value function thereafter, right? So you can kind of think of the Q function as one step reward plus following the policy thereafter, which is the Q is essentially equal to R plus some discount times V, right? And so V to Q is V is the expected Q. Q to V is there's like an expectation here, but in shorthand, you can write Q is equal to R plus gamma V. Go ahead, sir.
Maybe this is because I forgot the exact form of the reward function, but
Uh-huh.
the reward function needs to be weighted by like the dynamics.
Does the reward function need to be weighted by the dynamics? No, because you're yeah, I guess what you're saying is that the reward doesn't depend on S prime usually. The reward only depends on S and A. And so you can write like the Q function as the expected sum of rewards starting at S and A, right? And you can write this as the first reward plus the rest of the rewards, right? And so this thing doesn't depend on S prime. And so you can kind of take that out, right? So like basically you have an average over all the future states, but your current reward doesn't depend on your future states, right? And so you can say that your Q function is essentially your Q function is essentially your current reward plus gamma times the expected value in the future, where your next state is sampled according to the dynamics. Right? At least let's start with that intuitively, and I'll work it out more formally. But intuitively, you can kind of think of it as your Q value is saying you start at S, you take an action A, and then you follow the policy, right? And you can like have many different future states that you reach, right? But each of them, you start at state S, you take action A, and you get to, let's say you get to state S prime, right? The Q value of SA is essentially equal to the reward for the first step plus the value at the next step discounted. Right? So you're going to say QSA is RSA plus gamma times the expected value at the next step. Okay, we'll derive this formally, but let's start with just intuition. And intuition is like because it's like Markovian, right? It's like you can decompose things step by step. You're saying the Q value is saying take an action one step, not according to the policy, that's going to be an R, and then act according to the policy thereafter. So that's how you connect Q to V and V to Q. Right? Okay.
Sorry, I guess same question as, should I be imagining this function as being inside of an expectation of your dynamics?
So
Because there's a bunch of state primes.
Yeah.
That SA.
Yeah, that's a great question. So the V doesn't have an expectation under your dynamics when it comes to the Q. So it's like this thing has no expectation under the dynamics. This relationship between V and Q.
Right.
And when you connect Q and V, that'll have an expectation under the dynamics. So
I meant the equation you wrote at the bottom where you showed an R. It's really an expectation for that whole thing.
yeah. So this will be equal to like R of ST80 plus gamma of expectation ST plus 1 from your dynamics of V of ST plus 1. So like there's an expectation under the dynamics here.
R can also be stochastic.
R we're assuming is deterministic so far. But if R was stochastic, there would be an expectation there. So we're assuming that R doesn't depend on future state and R is deterministic right now. Right? And so yeah, it'll make a little more sense when we derive the whole thing, but the intuition is just like the Q value is like one step off and then act according to the policy, which is one step off plus the value, right? Okay, so that's how we connect Q and V. But the reason I introduced the V is just because the V is a little easier to think about. The V is just saying, what is the expected sum of rewards under my current policy, starting from my state ST. So the nice thing about the V is that it has some nice recursive properties, right? So a value function is your sum of rewards starting at ST and AT and then acting according to your policy in the future, right? So it's like essentially R of ST AT, but summed up from T to like capital T, right? So a value function is essentially the expectation of R of ST AT plus R of ST plus 1, AT plus 1, plus R of ST plus 2, AT plus 2, all the way till R of S capital T, A capital T, right? And so it's like a sum of all the rewards in the future. The nice thing about this, it's additive, right? So you can decompose the sum of rewards into the future as the first reward plus the sum of the rest of the rewards, right? So you can say like, this is the first reward and this is the sum of the rest of the rewards. Yeah. So you're just like taking a sequence of T things and breaking it up into like first and the rest. So that's basically all we're doing in this first line. We're breaking up into the first and then the rest. And then we can say, as we said earlier, like this reward doesn't depend on the future state. So you can write this as essentially the expectation of a reward plus the expected reward in the future, right? So you can say reward, it's reward now plus the expected reward in the future, right? So you can say that you can essentially move your expectation one inside. And what this allows you to do is you'll start seeing that this like is starting to look recursive, right? You can see that it's like reward now plus sum of rewards in the future. You can move the expectation inside because this doesn't depend on ST plus 1. And so now you have expected reward plus expected reward in the future, right? And so essentially, if you look at this thing, it is the value function, but at the future or in the future, right? And so what you can say then is that this is your V of ST plus 1, right? And so you can show that your V of ST is essentially your current reward, R of STAT, plus your future value, right? And so you're saying that this thing is your future value, this thing is your current reward, and you're taking an expectation over both the actions and your dynamics, right? So let's kind of decompose this a little bit more. And let's like make sure we didn't jump steps. Yeah. So I think it's helpful to expand these expectations a little bit, right? So a V pi is going to be an expectation of AT coming from your policy, ST plus 1 coming from your dynamics. And then like, let's say like all future actions and states came from like your policy and dynamics, right? And it's going to be like the sum of rewards, right? That is your value function. Now, what we did by decomposing this was we said this is going to be the expected action AT coming from your policy, your expected next state coming from your dynamics of your first reward plus your like sum of the next bunch of rewards, right? So all we did is we said, I just wanted to expand the expectation so we don't skip over steps. Yeah. So we're saying the expected sum of rewards, where your first action is sampled from your policy, your next dynamics is sampled from your dynamics, and then you keep sampling action, policy, action, or like dynamics, policy, dynamics, policy, dynamics, policy. And so this is just like the shorthand for, this is expanding the shorthand for expectation. Yeah. And now what we're saying is that we can decompose the reward into the first reward and then the rest of the reward. Now, the important thing to remember is that this thing does not depend on ST plus 1, which means that this expectation over ST plus 1 can move inside, right? And so the first term doesn't depend on ST plus 1, which is what allows you to move this expectation inside. Sorry, I'm going to go all over this board, but follow my arrows. But we're going to have expectation, but like R of STAT does depend on AT, right? And so you can't move the action expectation all the way inside. You can just move the next state expectation all the way inside. And so what this is going to simplify to is AT coming from pi theta of R of STAT plus an expectation over next state coming from the dynamics of the like sum of rewards in the future, right? And so all I did here was I wrote this out. I wrote out this expectation. This thing doesn't depend on ST plus 1, which means I can push this expectation inside. And then I just said like that this expanded is just going to be expectation under your actions of your first reward plus expectation of your dynamics and everything else of all the future rewards, right? And now this thing on the right-hand side is your value function, right? And so that's essentially what we've done is we've kind of like worked out these steps without shorthanding the expectation. But we've said that your value function now is your reward now plus your value function in the future. Right? So just like this is why it's dynamic programming. You're saying that you're like just recursing, like you're going backwards. You're saying like intuitively you can kind of think of it as if you have like a chain your value function now is your reward now plus your value function in the future, right? Does it make sense? This is like arguably the most important equation in all of reinforcement learning. So it's important that we get it right. Okay? And so there's a few caveats here. The first is that like you want to be careful that you're taking this expectation has actions, the first action coming from your policy, and then the next state coming from your dynamics. Now, if your dynamics was deterministic and your policy was deterministic, this wouldn't be a problem, right? But like make sure you're not ignoring the fact that it doesn't have to go to the same ST+1. It can go to many different ST+1s because it's stochastic dynamics, right? Which means that you have many possible futures. And then the second thing is that this equation, it's not an update. It's just like something that holds. Like if you have the true value function, like this thing holds. We haven't described how to learn it yet. It's just like this is something that holds for the definition of our value function. Okay? So this is what you call your Bellman equation. But your Bellman equation says your current value function is the expected reward plus the next value function. Yes. And so that's what you'll call your Bellman equation. Yes.
Spend more time while like on the top equation, is one condition on S2, the bottom one is condition on or below is condition on S2 plus 1.
Yeah. So my board space is a little. Do you mind if I draw on this whiteboard? So we have expectation of like the expectation on the top is the first action is drawn from pi theta, right? Of AT given ST. And your next state is drawn from P of ST+1 given ST and AT. And then you're going to have like all of the future things that I'll skip. And you're going to have like sum of R ST AT from T equal to T to capital T. Right? Now we're going to separate this thing out into R of ST AT plus a sum from T prime equal to T+1, capital T of R of ST prime AT. We just like separated this up. And now what I'm saying here is that this is like the reward. This is an expectation over the next state. And then the current reward doesn't depend on the next state, or like it doesn't affect the next state, right? So basically this thing is not dependent on the variable that you're taking the expectation with respect to in the next step, right? And so what that means is that you can push this expectation and everything else in the future inside. So like R of ST AT only depends on ST and AT, right? And so essentially like everything here can be pushed inside. Right, so it's like basically if you like if you want to write an integral form, right? So you can write this as a bunch of integrals, right? And then you'll have R of ST AT plus like sum T prime R of ST prime AT prime, right? You can kind of think of it as like the R affects the AT integral, but it's not going to affect the ST+1, ST+2, ST+3 integrals. And so like this thing has to stay within this integral, but it can come outside of all the other integrals. So you can push all the other integrals inside. Does that make sense?
Yeah, I think maybe I was a little more confused about the notation, but I think
No, let's go over it. Like which part of the notation is
like summation. So like that second like R of ST prime, AT prime is only conditioned on ST, but not ST+1.
This one.
Or the one above it.
So this thing is saying like what is the sum of rewards when you start, when I put this like right hand side bar, it's just saying like when you start at the state ST.
Okay.
And like then this thing is saying like the sum of rewards when you start at the state ST.
Yeah. That makes sense. Yeah. Thank you.
Yeah, of course.
What do we need for the words not depend on like the next state? I'm saying we don't really care about the of reaction or stuff like that.
No, so the states depend on the previous states and actions, but like basically R is a function of ST and AT and not a function of ST+1. Right. So like
an example would be like, let's say you're like mopping or something.
Uh-huh.
Building like electric use. Like the electrocution would happen in the next stage.
Yeah. So like I would incur that reward, but that's because I reached SC plus one, which is bad. Right. So it's kind of like if I was at this state, like the electrocution happens there. And I'm at this state and I'm not getting electrocuted now. I will get electrocuted, but not at ST80. I'll get electrocuted at ST.
Also then independent of what your AT is.
Exactly. That's right. So it'll hit you at ST plus one, not at ST. Okay. Been with me on this Bellman equation, right? It's just like dynamic programming with a bunch of expectations. That's it. Okay, and so as we discussed, we can also connect Q's to V's, right? And then it becomes kind of like easy to derive this once we've derived the or easier to derive this once we've derived the Bellman equation, because we can say I'm just going to write on the board again just for space. Because your Q function is essentially your expectation under a particular ST and AT. And you can decompose this into the first reward plus the sum of rewards in the future, right? And so then you can write this again as like essentially the reward plus the value in the future. So you can like kind of derive the same relationship between Q and V by doing the same process we did for the value recursion. You can also do it for the Q recursion. Okay, so the main points to remember: current value is expectation of current reward plus future value. And Q is essentially one step. This is what you call a one-step look ahead, where you say the Q value at some SC and AT is saying it's the expected reward plus discounted value in the future. When you start from state ST, take action AT and get the next state according to the dynamics, right? So your next state is coming according to your dynamics. So you're going to take reward SC80 and take the discounted value in the future according to the dynamics. Right? So that is the relationship between V and V at the next, and then this is the relationship between Q and V at the next. Okay, questions? Yeah.
Why can't we take the
You can. Yeah. So you just do that. Right. It's just I'd have to like re-LaTeX my slides and that stuff. Okay. So this is what we call your Bellman equation, right?
Quick question.
Yes.
Is there a LaTeX for slides or?
I LaTeX it separately and then paste it. Because like the PowerPoint LaTeX is not very good. So that's how much hard work I put into this class. Right? Okay, so we figured out that value functions are recursive. And the recursive thing, your current value function is equal to the expected reward plus the future value function. And so essentially what we're going to try and do is we're going to try and like convert this. This currently is just an equivalence. We're going to try and convert this equivalence into an update, into an objective that we can optimize. Right? So this is an equivalence that hasn't told us anything about how to learn a VPI. What we're going to try and do is we're going to try and convert that into an objective that we can use to learn a VPI and then use the VPI for policy grading. Okay. So the steps we're going to take is we're going to figure out how to convert that recursion into an objective. Then we're going to figure out a way to stick that learned VPI into policy grading to make it better. Okay. So two things we're going to do. The first thing is we're going to try and convert this into an objective. We'll unpack this objective in a second. And then the second thing we're going to do is we're going to try and stick that learned thing back into policy gradient to make it better. Okay, so let's go over the objective first on how do we learn a value function, and then we'll stick it into policy gradient. Okay, so the objective we're going to do here is we're going to say, we're going to construct targets, and we're going to call these YIs, right? So YIs are going to be our targets. And a YI is basically your reward plus V at the next step, right? So given a set of transition tuples, let's call them SI, AI, SI prime, right? Or SI prime. Basically, it's your current state, an action, and the next state that you got according to the dynamics. What we're going to do is we're going to construct targets, which are basically your current reward plus your next value, right? And then you're going to try and regress a function onto like this target, which is current state plus your next value, right? And so essentially what you're going, like the way you can think about it is you're going to sample a tuple, a set of tuples of S, Si, Ai, Si prime. And you'll also sample like the rewards that you saw during that transition. Then for each of these tuples, you're going to construct a target Yi, right? So your target Yi is going to be Ri plus, there should be a discount here, but discount times your future Si prime, right? And that's going to be your target. And so for every tuple, you're going to construct a target. So you're going to have like k different tuples. For each of them, you're going to construct a target, which is your current reward plus gamma times v of your next state. And then what you're going to try and do is you're going to like treat these targets as the targets for a supervised learning problem. As Kunal was saying, everything is supervised learning. So we're going to like convert these. We're going to take like every tuple, we're going to convert it into a target, which our target is going to be reward plus future value. And then we're going to try and regress. We're going to try and learn a function that goes from your Si to your target. Yeah.
Where do you need the V?
Yeah.
You need the V.
Mhm. Yeah.
So do you use the previous?
Yeah, good question. So Sid has foreshadowed what Ola is going to get to in a second. But basically, the important thing in this procedure is you're constructing the target. You're saying the target is your current reward, or your reward at that tuple plus gamma times your current value function at Si prime, right? So this is going to be an iterative process. You're going to have a particular value function. You're going to use that value function to construct targets, right? And then you're going to try and regress onto those targets to get a new value function. And then you'll repeat this process with the new value function. Right? And so essentially it's what you call value iteration, or loosely value iteration. Essentially you're saying, take like the cleanest way to write this is that you're going to like take your value at iteration I, and you're going to stick that in to get your targets. And then you're going to use that to update to get a value I plus 1. And then you'll stick it back in, right? And so I specifically constructed these targets and for a reason, and I didn't just stick it into this objective. But the important part is you're going to take your current value, construct targets, use that to regress onto something that will be your new value, and then stick that back in to construct new targets and repeat.
Is it possible for this iterative process to suffer?
It can suffer from divergence, which is kind of like compounding errors. Like it can, like you're doing this iterative process where you're starting from V, then you're like constructing targets and updating to another V, it may not converge. And you can show that it converges for certain settings and doesn't for others. And so like that's the analog of compounding. But that's a good question. Yeah. Okay, so the important thing here is that when I'm constructing these targets, I am not taking the gradient through this value function, right? So I'm only, you can kind of think of this as like, if you're in PyTorch, you like do it with stop gradient, right? So what you do is you like construct a target, you stop the gradient through this guy, and then you regress on a particular value function. Once the value function is good enough, you construct a new set of targets, right? But you do not take the gradient through the right-hand side. And there's a bunch of reasons for that, but the simplest way to understand it is that it's like, you're trying to prevent this chase your tail scenario that Sid was talking about. Like you don't want the right and the left-hand side of your equation. And so what you do is you like freeze your targets for a while, you do regression, then you update your targets. Then you freeze your targets for a while, you do regression, then you update your targets, right? And so you can kind of think of it as this procedure where you take your previous value function, construct targets, regress onto them, get a better value function, swap it in. That's what I call value iteration. Does that kind of make sense as a procedure? Now, the weird thing about this procedure is that it is not supervised learning. Every time you do regression, it is supervised learning, but then you like change your supervised learning problem. And so you do VI, you construct targets, you do regression, and then you like change VI again, right? And so it's kind of like you're solving a series of supervised learning problems, but it's not like supervised learning where you're just doing gradient descent or ascent on a single objective, right? And so the reason reinforcement learning with dynamic programming is much harder to understand is because it's not gradient descent. It's like this weird iteration process where you're doing like regression, change the problem, regression, change the problem, regression, change the problem. So it's not a well-defined, like minimization problem. It's more like a procedure. And you can, we'll study in like next class that we can show that this procedure converges sometimes. Okay, does that kind of make sense as a scheme? At least from a mechanistic standpoint, you start by you initialize your value functions, you construct targets, you regress onto the targets, and then you update your value function. Right? This gives me, you repeat this process over and over and over. Believe me, without proof that it'll converge in certain cases, and we'll talk about why. But once you have the value function, then you're going to use it to improve policy gradient. Yeah. Okay, so how would we use it to improve policy gradient? So now you've done this procedure. You're going to get a V that comes out of it. Right? You're going to get a value function. Value function is great. So value function is good. We have this. We're happy. How do I use it to improve? But I care about policies that can act in the world, right? So how am I going to use my value function to update my policy? So what I want y'all to look at is like, look at the policy gradient update on top. And how do I use a value function to make it better? Or maybe look at the version of policy gradient where you had like sum of reward. So I want to make that better. How do I do it? Yeah. So the first idea is you could use it as a baseline to reduce variance, right? Like same as we were doing before. But if you just substitute it as the sum of rewards, the problem is it doesn't account for, because it's the average over all the actions, it doesn't tell you how much better that particular action was than the average, right? And so you have to do, like the thing to look at is how, like if you remember, we connected Q's and V's, right? And so what we're going to do is we want something that looks like Q, which is telling us how good was this action at this state, right? And a V is more like how good was the average policy, right? And so what we're going to try and do instead is use our relationship between Q and V to improve the policy gradient. So we are going to do a one-step look ahead. So if you remember from the previous slide, right, we said the Q's and V's are connected by this one-step look ahead. The Q at any time step is the expectation of the reward plus the value function at the next time step. And so what we're going to do here is we're just going to do one-step look ahead, where we're going to say the Q is the reward function now plus the value function in the future minus like a baseline, right? And so this is essentially going to be your estimate for Q, like a one-step look ahead. And intuitively, you can kind of think of it as like, maybe I have it on here. Ah, good. You can kind of think of it as like you're taking your state ST, you're doing like a single step of reward. And then you're like, instead of doing a single sample estimate, you're like substituting in your value, which is kind of like an average, right? And so you're making your policy gradient better because you're not doing a single sample estimate on the rewards in that trajectory. Instead, you're saying you're going to take your 1R for that one time step and then have like a function approximated V. So it's going to do this like sharing thing that you want. So essentially you're getting closer to something that does this like this averaging. Okay. So it's like one step look ahead plus the average value at the next state. Yeah. And so the main change you're going to make to policy gradient is you're going to replace your sum of rewards with your reward plus your next value minus your V as your baseline. So the main points, this is what you'd call like value iteration and estimating your value through value iteration. Essentially what we're going to do here, we're going to do this iteration process, which is relying on this like Bellman update. So the Bellman update says V is equal to expected R plus next V. We've converted that into an update. Right? The important thing to remember is the update is not gradient descent. It is related, but it's not gradient descent. but you're going to do this iterative thing of constructing targets, regressing, constructing targets, regressing. And then you're going to use that to improve your policy gradient with a one-step look ahead.
How do you get ST plus one? Because you don't have dynamics. So
But you have trajectories, right? So you took like entire trajectories from your data set. Like you ran things in the world, right? So you know you were at ST, AT, and you got to an ST plus one. So you don't have dynamics, but you have samples from dynamics.
I see. Okay.
How does this solve like the optimized issue?
It doesn't. It doesn't.
Pretty much
Yeah,
what I'm trying to get at.
Yeah, it doesn't solve the on-policy issue. It solves the variance issue, but it doesn't solve the on-policy issue, right? So it's using this dynamic programming thing, so it can like bootstrap things, like it can use function approximation across time to reduce variance, but it doesn't solve the on-policy issue. Very astute. That's good. Yes.
In case you need to keep track of the older values in the space, so when we have memory consumption.
Well, here you're not keeping a table. You're going to like learn a function approximator. So it's like, yeah, but like the original version of value iteration will keep a table, and then your like thing grows up with states. Yeah, absolutely. Do you have a question? No. Okay, so as you guys astutely noted, it's still on policy, but it is at least lower variance, right? And so we're going to try and fix that. But essentially, the procedure looks like fit a value function from on policy data, compute the policy gradient, collect more data, and repeat. And within this process of fitting a value function from on policy data, you're not going to minimize this objective once, you're going to do it many times, right? So you're going to solve this regression, update the target, solve this regression, update the target, solve this regression. You're going to do this many, many times. Then you're going to update the policy grid, collect more data, and then repeat. Right? So as you said, it's still on policy, but it's lower variance, right? So it lowers variance because it uses this like recursive structure to share more information across timestamps, but it's still on policy. And we really like the whole lecture is called off policy audit, so we have to get to off policy audit. But it's better than where we're at. Okay, questions? Does that make sense? So really the essence of this part of the lecture is that the value function has recursive structure, right? So value function has recursive structure, that's your Bellman update. You can convert the recursive structure into an iterative update, and you can use that to reduce variance with this one-step look ahead. Yeah. Okay. Good. Are we ready to move to truly off-policy things? Sweet. So our issue is that we are still on policy, right? And so the next set of methods, which are often called Q-learning methods, sometimes actor critic, we have to get better at naming things, but I would call them Q-learning style methods. And really what Q-learning style methods are trying to do is take that recursive update we had, and instead of doing it on the value function, do it directly on the Q function. Okay? So the Q function, as you remember, is starting from state ST, take your first action AT, and then follow your policy. We're trying to say there exists a recursion which is directly from on Q to Q, right? And so we're going to try and derive that recursion. And so a Q function is the sum of the first reward plus the expected sum of rewards in the future, right? And so again, we like want to make sure we get the details right here. So I'm going to write on the board again. Oh, actually, I have a lot of space on the slide. Okay, so we can just write on the slide. But what we're going to try and do is let me like not shorthand the expectation, right? So we're going to say, in this expectation, your ST is equal to ST, your AT is equal to AT, your ST plus 1 is going to be sampled according to your dynamics. Your AT plus 1 is going to be sampled according to your policy, and so on, right? That is your expectation. And you're going to say that is your sum of rewards from T equal to T to capital T, right? That is what our Q function is. So you're starting at ST, you're acting according to AT, and then you're following dynamics policy, dynamics policy, dynamics policy, right? Now you can again do this thing where you break up the rewards. Let's say you broke them up as reward at the current time step, R of ST plus sum of rewards at future time steps, right? R of ST prime AT prime. Right? So you just broke it up into the first and the rest. Yeah. Now you can just move everything after here in like those expectation terms. R of STAT doesn't depend on them. So you move them all inside. Yeah. And so what that is going to result in is you're going to have essentially R of STAT comes all the way out. Like ST is fixed, AT is fixed, right? So it's going to be R of STAT comes all the way out. And then you're going to have an expectation, but remember it's over ST plus 1 sampled from your dynamics and AT plus 1 sampled from your policy at ST plus 1. And then everything else, right? So, and then you're going to have like the sum of future rewards. So all we did is we said this thing doesn't depend on ST plus 1 onwards. Move everything in this expectation all the way inside, right? And so you're going to say your Q function is equal to your reward now plus the expected sum of rewards in the future, where your next state is sampled from the dynamics and your next action is sampled from the policy. Now, if you want to do a recursion directly onto the Q functions, right? Like this thing is not, it's like, it looks almost like a Q function, but it's not exactly a Q function, right? It's not a Q function. Like what is making it not a Q function? So it's like expected sum of rewards in the future, but sampling ST plus 1 from your P and AT plus 1 from your policy. And so why is it not exactly a Q function? Okay, so just to recap, we wrote out the expectation non-shorthand. We separated R and the rest of the R's. And then we said that this thing doesn't depend on ST plus 1 onwards. So you move the expectation inside. But here you're going to say your ST plus 1 is sampled from your dynamics, and your AT plus 1 is sampled from your policy. And you're going to say, follow the policy thereafter. But it is not the Q function. It's not exactly the Q function at the next step. Why not?
Because we sample the action from the policy.
Perfect. You sample the actions from the policy, right? And so instead, what it's going to be is it's going to be the average Q function at the next step with the action sample from the policy, right? And so what it's going to be is not just the Q function, but instead the average Q function at the next step, where the ST plus 1 is sampled from the dynamics and the AT plus 1 is sampled from the policy. And so remember, a Q function is start at ST, take one AT that's off, and then follow the policy, right? And so this thing is not going to it's not just going to follow the policy, it's not quite the Q function, it's the average Q function. And so your Q Bellman update is going to be Q pi STAT is your first reward, plus the expected Q in the future, where the expectation is taken for ST plus 1 from your dynamics and AT plus 1 from your policy. Does that make sense? So this is essentially, you can also think of this thing as like expectation of ST plus 1 of your value. Those are like the same. Those are the same thing, right? But we want to write our recursion in terms of Q. We don't want to, and I'll explain what, but we basically don't want to have any values in the mix for now. We're just going to do everything according to Q, right? So Q pi is R plus expected Q in the future, where ST plus 1 comes from dynamics and AT plus 1 comes from your policy. Okay, everyone with me?
So the distinction is that it's not, like the term you're saying, it's not exactly a Q function.
It's like the average Q function.
Okay.
Yeah, it's just like, but it's important because it's like the Q function where your actions are sampled from your policy pi theta. But it's not like under some arbitrary actions, actions under your policy pi theta. Right. So if I'm trying to evaluate Q pi, like this expectation has to be with action sampled from pi. Right. So what makes this off policy, right? Well, why this is gonna enable us to have an off policy update is because your AT here and your AT here can come from different policies, right? So you're saying like the Q function allows you to take one action that is not from a policy and then take the rest of the things from the policy, right? So it's saying that this first action doesn't have to be from your current policy. It can be anything. and everything else in the future has to be from your policy. Right? And so what allows this to be off policy is that you can stick in different things here and here. Right? Your Q function, you're allowing it to take one step, which is not according to your latest current policy, right? And so, like this recursion is going to allow you to evaluate policies by, but with data from not by. Right? So you're going to have data from some other thing, which is not by. And because you can stick in arbitrary actions here, which don't have to be from pi, this is going to allow you to evaluate this thing on transitions which are not from pi. Like they have to be from the same environment, they have to be from the same dynamics, but at least the policy can be different. And that's what makes it off policy, right? And so the magic sauce in the Q function is that it allows you to take one step according to AT, which doesn't have to be from pi. Okay? It's a little bit counterintuitive, but one way you can think about it is that you're allowing it to take one step according to some AT. And let's say your data set was pretty biased towards going this way. Let's say you had a lot of your data set going this way, and you're trying to evaluate a policy that is going this way, right? You in your Q function, you can stick in something that doesn't act according to the policy or according to the most likely things in the policy. You can stick in whatever you want, okay? And after that, you have to follow the policy. So what allows this to work is just that separation between the first action and the other actions. Yeah.
I guess, consider, so the Q function is trained on.
Yeah, should I go through the objective? This is just an equivalence. I haven't gone to the objective yet to frame Q. Would it make sense after? Maybe let me go through that and then, yeah. Okay, so this is the equivalence. The same way we drew a value equivalence, we've drawn a Q equivalence now, right? Like Q pi is R plus expected Q in the future, where ST plus 1 is coming from P, and AP plus 1 is coming from the policy that you're trying to evaluate, right? And so it's going to allow us to be off policy. And so essentially what we're going to try and do is convert this into an update the same way as we did before. And so what we're going to do is we're going to say you have Q pi of STAT. You want it to be as similar as possible to R of STAT plus the expected Q at ST plus 1 sample from your data, from your dynamics, and AT plus 1 sample from your policy. Okay, so the full update is going to look like you sample ST, AT, ST plus 1 from your data, which means that the ST plus 1 is according to the dynamics. It has to be, it's in the same environment. So it's from the dynamics, right? But D does not have to be pi. It does not have to come from pi. It can come from anything else. Yeah. And that's why it's off policy. But your data set does not have to be pi. And then what you're going to do is you're going to try and make Q pi of STAT as close as possible to R of STAT plus the average Q of ST plus 1 evaluated at AT plus 1 sample from your policy, right? So remember that this next action is not something you saw in the data set. The next action is sample from the policy, right? But you don't have to run it. The important thing is you don't have to run AT plus 1 in the world. You just have to stick in AT plus 1 into your Q function, right? And so the reason this is off policy is because I never have to run pi. I just need to stick in pi into my Q, and I can get my data from something that is not pi. The data can come from something else, but I can evaluate a pi, right? And so that's what allows this to be off policy. And so yeah, so this is the important part of this update is that this thing is not pi, but this thing is pi. And so when you're trying to evaluate a particular policy pi, the main thing is that in your Bellman update, make sure that your target or the things that you're constructing on the right-hand side, the targets like we did earlier, are sampling actions according to pi. But your data doesn't have to be according to pi. Okay. Questions? Yes.
Wouldn't this still mean that if your pi changes, you still have to be?
Yes. You still have to recompute it, but you don't have to recollect the data. Right. So the way that this procedure will typically work is that you have a pi, you evaluate it with it, solve this thing, and then you take an update, your pi changes, and then you reevaluate it. but you don't have to keep recollecting all the same data, and you can use your prior data. Right? And so that the nice part is that D doesn't have to come from pi. Like the totally practical version of this is that you approximate inserting an expectation over AT plus 1 with many samples. You approximate it with a single sample AT plus 1 from your policy. And so like the objective that you'll implement in your homework and like is often used is essentially this objective where you say you sample ST, AT, ST plus 1 from some data set that doesn't have to be pi. And you try to make Q as close as possible to R plus Q at the next state with an action sample from your policy. And so the way you're going to implement this in practice is you'll have a data set, you'll get ST, AT, ST plus 1. And then you'll take ST plus 1, you'll stick it into your policy, you'll get an AT plus 1. Right? And then you stick in all of these things into like the appropriate places in this thing. And then you like minimize, right? The other important thing to remember in this update is like, just like we did for value iteration, you're constructing targets and regressing. It's not like you're passing gradients through here. So if you notice that this is phi and this is phi hat, right? So like, that's not quite the same thing. So it's more like you're constructing targets and then you're trying to regress onto the targets. So there's no gradient going through here, right? So the only gradient is going through here. That's it. I guess it's kind of Q value iteration.
So,
But you're not doing, there's no value function per se.
yeah, so Q iteration.
Q iteration.
So this does not require me to use data that comes from the policy.
Yeah.
And meaning that I can use either old data or my data that's collected elsewhere.
That's right.
It does, however, require the other question I had was estimating the Q itself should require data from the policy. Right?
You don't need to have like this is estimating Q. Like this thing is the objective to estimate Q. And so you can do it without data from your policy. You just need to have, what you need to have is access to a policy which can sample so that you can stick it into the right-hand side. And you need to have data under the same dynamics, right? So you need to have data which is sampled in your environment, but it can be according to a different policy. So often you like the data set D is sampled from a policy you call your behavior policy, and your behavior policy doesn't have to be the same as the policy that you're evaluating, right? So to Rico's question from earlier, you like collect some data, you want to take an update, like your policy might keep changing, but your old data is no longer invalid. Like for PPO, you could only use it for some steps. For policy gradient, you couldn't use anything. Here, you can keep using that data. That's what makes it cool. But it's not a silver bullet, right? So like the important thing is that if you have a policy that is extremely different from your behavior policy, then like you will start sticking in things into your right-hand side that were never seen on your left-hand side. And you'll start like getting really bad artifacts, right? So it's not gonna, you can't just like, it's like, I can't just like have all this data walking over there and ask what's gonna happen over here. Like you have to have some overlap in the data. And the way that it manifests is that if I'm going to query my Q function in an action that has never been seen over here, then I'm like in trouble, right? Because you're asking a question that is not in the data. And so you can like, it's more like you can consider training on reweightings. Like there has to be some overlap between your D and your pi, but D doesn't have to literally be pi. But if there's no overlap, then you're going to query your Q on out of distribution things, and then you have problems, right? And so that's kind of the like trade-off here. Okay, so you stick in a neural net into both of these things, right? But in this version of the algorithm, remember that you're doing a stop gradient here. You're not passing the gradient through here. You're just using this to construct targets and only passing the gradient in through here. Right? So like the same way as in value iteration, you constructed R plus gamma V targets, you set them as Ys, you stop the gradient through this thing, and then you regressed. You're going to do the same thing here. Instead of R plus gamma V, you're going to do R plus gamma Q S prime A prime. Right? You're going to set those as your targets, do a regression, regress a bunch, and then you're going to swap out your Q function again. So the same procedure. Targets, regress, swap out your Q function, repeat, right? So it may look like gradient descent, and almost deceptively so, right? Like I'm just saying there's a minimization, but the important thing is that every so often you have to swap out the stop gradient and you have to swap out the right-hand side. So it's more like this iteration process. There's like explanations we can get into, but like that's kind of the main point here, right? You're going to do this iteration process. That's going to give you a Q. Your data doesn't have to come from pi, but you just have to sample from pi. And so that's why this is off policy, and it's going to use your temporal structure, which is going to let you be low variance. And we will get to policy improvement. How do I use this for policy grade next time? But like the main thing you should ponder for this class is like why this thing allows you to be off policy. Like, I would recommend trying to draw a graph and like work this out with the graph, and it'll start to make more intuitive sense. But I'll go over that in the start of next class, but try to work it out yourself this. Got a question?
But does this mean that for every policy gradient step, we now need to sort of complete neural network?
Yeah. Yeah. So for every like you have to update your Q function every time you update your policy. But what you often do is you keep like a warm start.
Yeah.
And so you don't start it from scratch. You just keep your previous update, you do a little gradient update here, a little gradient update here. And so you kind of run those things together.
Basically, we train a whole neural network just for one gradient update.
But the next time you don't like start it from scratch, right? You just do a little update on the Q. Cool. All right. Thanks, folks. Homework 2 will be released maybe over the weekend, just so that you have some more time to digest this, and then you'll have more time. Great. Thanks.
You can only use a single dynamic.
Let's
So
find
like,
for the first
if you actually want to test.
Yeah.